This is the start of a new unit, and this is chapter 13, all about chemical kinetics, which is simply about the rate or speed of reactions. And we have, there are either 5 or 6 lectures in this chapter. This first one is just an introduction. So definition for kinetics, again, it's just a study of the rates of chemical reaction, how fast or slow they go. And just like any rate or speed, it is the change in concentration of a reactant, or it could be from the perspective of a product, concentration change per unit time. So just like the speed at which you travel in your car is the number of miles, or the change in the miles you've traveled over time, the rate of reaction is change in concentration over time. And so you'll see plots similar to this, where the y-axis is change in concentration, is concentration period, and the x-axis is time. And obviously the rate of a reaction with respect to a reactant is going to decrease over time. Just to kind of remind you again, this is some of the vocabulary and symbols. Brackets mean concentration, specifically in terms of molarity, and so you'll see a lot of that in the kinetic equations. And rate or speed of reaction can be in terms of reactant or product. If it's in terms of reactant, it'll be a minus sign because the reactant decreases over time. If it's in terms of the product, it'll have a positive sign because the product is increasing over time. It's building up. So this is showing it in mathematical terms. Products have a plus sign. Reactants have a minus sign. The units for the rate of reaction, since it's the change in concentration over change in time, the units are molarity over some unit of time, seconds or minutes. So if you plot concentration of, my little stylus isn't working, reactant versus time, it's not a straight line, it is a curved line. So basically, the rate, which is the slope of this, decreases over time, okay? So rate slows down over time, okay? That makes sense because what determines the speed of a reaction? It's determined by, in part, by how many reactants are available to actually collide with each other. If you have a lot of reactants present, they're crowded, there's going to be a lot of collision and a lot of product. If you have fewer reactants, they're going to encounter each other less often, and so there'll be fewer collisions, less product made, and a slower overall rate. And at some point, every reaction either reaches the end of the reaction, it's run out of reactions, but more likely in that it reaches an equilibrium. So we can talk about that, we'll get into that later, but just kind of to introduce the concept, if you have reactant going to product, usually a reaction is reversible. So once you start building up enough product, you can generate collisions between the product and they can go back to reform reactant. So when you have both processes going on and there's no net change, that is considered to be equilibrium. And once you have no net change, it's for all purposes stopped. So again, I mentioned this before, but the reaction rate is the change in the concentration, which is the y-axis, over the change in time, how much time has elapsed. So it is the slope, and you can see that the rate of most reactions, almost all, virtually all, decrease with time. Okay, that slope gets shallower and shallower, and again, it's because you're running out of reactant molecules. So because the rate is constantly changing, it starts out high and continues to decrease. Where do you measure it? If it's constantly changing, what rate do you report? And so there are a couple different points at which rate is recorded, but obviously the scientist has to be very clear about where it is. And one of them is called an instantaneous rate, and those are typically done very, very early on. But the instantaneous rate is if you draw a line tangent to the curve. So this would be a line tangent to the curve. It just touches the curve in one place. So this, for example, would be the instantaneous rate at the point at which it touches, which in this case is, I don't know, 9 seconds or something. And so that's one way to report rate. You could also report an average rate where you measure it at several points and over a period of time and take the average. So there is math and some calculations we'll get into, but first it's important to be able to express the rate in terms of the symbols that chemists use. So as I mentioned earlier, you can describe the rate in terms of reactants or products, but there's a little bit of difference in how you portray it depending on whether you're talking about a reactant or product. And what's important when doing that is to know the stoichiometry of the reaction. So you need to start with a balanced reaction. So for instance, let's look at the dissociation of hydrobromic acid into hydrogen and bromine gases. So HBr obviously is going to decrease in concentration over the time, so the rate would be expressed with a negative value. If you express the rate in terms of either one of the products, they would be increasing over the time, so the rate would have a plus sign. They would also be increasing at the same rate because of the one-to-one stoichiometry between hydrogen and bromine. I ask you a question to ponder for a moment. Will the disappearance of HBr occur at the same rate as the appearance of the products, or might it disappear at a different rate than the products appear? Think on that for a moment if you can understand the question. And then I am going to tell you that actually hydrobromic acid, well, in this case hydrogen bromide, because it's not aqueous, will disappear 2 times faster than hydrogen and bromine gas will appear. So for every 2 HBr that react, you only get 1 of each of these. And so that's reflected when you write the rate expressions for this reaction. What this equation means at the bottom, and you may well have to think over it and ponder it for a moment because it confuses a lot of people, but make sure you understand it. It is important. In order for the rate with respect to the reactant, HBr, to be equal to the rate with respect to one of the products, we have to put this 1/2. Okay? Since the rate with respect to HBr is twice as fast as the rate with respect to H2, in order to be equal, we've got to divide by 1/2 since it's twice as fast. Okay? So there's a general equation that you can use which is things a little bit more simple. If this were a generic reaction, and you wanted to express the rate of this reaction with respect to each one of the reactants and products, this would be what you would do. Notice that you take the coefficient in front of the reactant or product that you're talking about, and the rate expression becomes 1 over whatever that coefficient is. So for the rate with respect to A, it's 1 over its coefficient. Make sure you have a minus sign if there are reactants you're talking about, and a understood plus sign if it's products you're talking about. So this is important, okay? It's probably the first really important concept to get. Graphical interpretation is always part of pretty much every unit. And so I have shown you this type of graph for explaining what happens to a reactant over time. I want you to see also what the graph would look like if it includes reactants and products. So here's the reaction we're looking at. It's actually how industry produces ammonia, which is very common intermediate for a lot of things in industry. So we have concentration in the y-axis, time on the x-axis, and the slope of all of these would be the rate. So we have looked at the production, at the disappearance of reactants before, and that is always a downward sloping curve with any reactant. Now I would pause a minute and ask you, why are these curves different? The curve of hydrogen seems to be more steep. So if I were to draw a line tangent to the hydrogen line, I would guess the rate of disappearance is quite a bit faster than the rate of disappearance of nitrogen. Why is that? It's always due to stoichiometry. So you can see by looking at the stoichiometry that hydrogen is going to disappear 3 times faster than nitrogen, and that's what you're seeing in the difference in these lines. Let's look at the product for a minute, the rate with respect to the formation of ammonia. Of course, products increase over time, so you should see an upward curving line for products. And ammonia, the rate of production of ammonia lies somewhere in between the rate of disappearance of nitrogen and the rate of disappearance of hydrogen. So if you were to take tangent lines to all of these 3 curves, the slope of those tangent lines should match up very nicely with the stoichiometry of the equation. Here's an example problem where you can see if you've kind of picked up the concept that I'm trying to convey. Look at this reaction. It's got a lot of reactants and products, so there's a lot of room for practice. The given information is they tell you that the rate of the reaction with respect to permanganate is 2.2 times 10 to the minus third molar per second. I hear my dogs tromping around. That's a dog drinking, if you hear that. What is the overall rate of reaction? So what do they mean by that? Well, if you talk about the rate of reaction with respect to a particular reactant or product, you've got to look at all the coefficients. If you see an expression that just says rate of reaction, it's not with respect to anything in particular, it would be the rate without any coefficient. So you would just adjust for that. And I'll work through that. I imagine at this point that probably doesn't make much sense to you. And then it would like you to calculate the rate of disappearance with respect to hydrogen peroxide. So they've given it to you with respect to permanganate. Now they'd like you to express it with respect to hydrogen peroxide. And of course, all of that is tied into the stoichiometry or coefficients. So if you think you have any idea of how to do it, give it a shot. Otherwise, I'll go over how to do it on the next page. Well, remember that I told you that the rate expression is always change in the concentration of either a reactant or product over the time elapsed. But then what goes in front of that change in concentration per time is 1 over the coefficient for that reactant or product. And in the case of permanganate, that's a 2. Is the minus sign because it's a reactant. And so that equals the rate. So if you just actually plug in the numbers, and they told you that the rate with respect to permanganate is minus 0.002. So if you just do that simple calculation, the simple rate, not with respect to any reactant or product, I have to get a new stylus, is here. Okay? There should be there, molarity per second. My units are off. And my doggies are letting themselves be known, slowly but surely. So B, part B of this question, calculate the reaction rate with respect to the disappearance of hydrogen peroxide. This one is probably the most important type of calculation, so make sure you understand how it's calculated. So if you're given the rate, the general rate, or the rate with respect to any other reactant or product, and asked to calculate the rate with respect to a different reactant or product, just make sure you set it up like I told you to. So in this case, with respect to hydrogen peroxide, look for the coefficient. Hydrogen peroxide is 5. It's a reactant, so there's a minus sign. Carry out that calculation, and you will find the rate with respect to hydrogen peroxide is minus 0.0055 molarity per second. It's that simple, but it's kind of easy to mess up, to tell you the truth. There are a lot of mistakes on that, so make sure you know what you're doing. Moving on to some other factors in the introduction of kinetics. And what are the factors that affect reaction rate? Well, probably the most front and center is the concentration of reactants. So in general, in fact, virtually always, the larger the concentration of the reactant, the faster the reaction. We'll talk about something called collision theory later, but basically the more reactants you have, the more frequently they encounter each other, and the more product you make. If you have gases, as always, pressure is a factor anytime you have gases. So concentration and pressure of gases are directly proportional. So as pressure goes up, concentration goes up, and rate of reaction goes up. Temperature is another very important factor in the rate of reaction. Increasing the temperature always increases the rate of reaction. So there's kind of a little rule of thumb for chemists, and that's shown here, that roughly, and that might help you out in a pinch later on, maybe on a quiz or a test when you're trying to estimate, but for about each 10 degrees rise in temperature, the speed of the reaction roughly doubles, and that holds pretty true. There's a mathematical relationship where you can calculate change in rates as a function of temperature, and we'll look at that later, but just introducing this dude. He's Arrhenius. He did a lot of work with respect to kinetics and rates of reaction. And another thing that will affect the rate of reaction is a catalyst, which you, I would think, have heard of, probably in biology. I know enzymes are reaction catalysts. So a catalyst is anything that speeds up a reaction without being consumed itself. Okay? So you dump a catalyst in and you can recover it at the end untouched. So it's kind of used as a crutch to speed up a reaction, but doesn't get used up. There are different types of catalysts, and you should know the terminology. There's what we call a homogeneous catalyst, which if you were to look at the reaction mixture, you wouldn't know it was there. So if you have let's say a liquid reaction mixture, the homogeneous catalyst would dissolve or somehow not show up. Then there are heterogeneous catalysts. You can put, there are some reactions where you can put in solid carbon, which just looks like those charcoal briquettes that you have in your grill. And those serve to catalyze some reactions, but they sit as a black solid glob at the bottom. And we'll talk about how catalysts work later on. And that is it for the introductory lecture in Chapter 13, Kinetics. So there'll be a short quiz on learning catalytics over this introductory lecture, so make sure that you take that by the time that it's due, and then look for the next lecture, which will be called Differential Rate Laws.